Welcome to the next talk. We have Johan van der Meer. He's a neuroscientist currently working at the QIMR Berghofer Medical Research Institute in Brisbane. And he's been fascinated with Python, which has recently been strengthened by having chosen to use it for some of his own research on brain-computer interfacing and neurofeedback training, which is what he's talking about today. So let's welcome Johan.
Thanks very much also for the chance to present some of the things that I've been doing in Python. The outline of my talk. In the beginning, I will talk a little bit about the signals from the brain. What are they? What they are composed of? What we're doing with them, and how to analyze them. Then in a BCI context, as a brain-computer interface, what kind of things can you do with these signals? Then I will very shortly touch a little bit on what kind of research questions I am occupied with. But I guess the main meat of the talk is how I use Python to further my research goals. So I hope to explain that. Bear in mind, I've only been seriously programming in Python for about a year or so. So if I show any code and you think, oh, this is really, really ugly, you'll be forgiving. All right. So first the BCI and what it is. In the way that I use it, basically it's a loop between the brain, a device with which you measure brain activity, real-time analysis of these signals, and some audio or visual feedback stimulus that you put back into the brain. Well, it's not directly, it's like more or less indirectly. You sound a beep, or you change some visual properties of a stimulus that you then see or hear. But anyway, it comes back into the brain. The EEG signal, it is generated because the brain is composed of many neurons, several billions of neurons. When neurons fire, that is like the basic building block of like brain function and cognition. Electrically charged ions start flowing from the extracellular space into the neuron, and this generates kind of like an electrical field. Well, the field of one neuron is kind of small. If many neurons are firing simultaneously, it generates a net magnetic field that you can measure even outside of the brain on top of the scalp with an electrode. You can measure the brain signal from many different positions on the brain, and that gives you your EEG signal that we are working with. This is an example of EEG signal. The first 5 seconds, the participant has the eyes open, and the last 5 seconds the participant has the eyes closed. So the signal properties, as you can clearly see, it changes depending on what people are currently doing. So this is kind of like internally generated change in the properties of your brain signal. A slight remark about the EEG signal. Because we're measuring outside of the scalp, or outside of the brain, on top of the scalp basically, the quality of the signal is not great. So I have a picture here of like a neighbor playing very loud music. The EEG, you can compare it with that you are in the middle of the middle house and you hear the music from your neighbor, but you don't really hear all the interesting bits of the music. You might hear when the music starts, you might hear when the music stops, and you might hear that your neighbor changes the music, and you wish he would stop, but the amount of information that you can get is a little bit limited. So then some words on how these signals are analyzed. Well, most often used, or maybe not most often, but an often used method is frequency analysis. So basically you look at all kinds of different types of waves. You have more slow waves, and you have a little bit faster waves, you have even faster waves even still, and probably the more faster waves that you can measure. The scale is 1 second. The algorithm, as you see, it's like 10 oscillations per second. And this is the rhythm that's most prominently present in EEG signal if you close your eyes. In most people, not everybody. And what researchers are looking at is, with these different kinds of waves, how much of these waves are present in the signal. What is also looked at is where inside this wave are you currently at? Are you at the top or at the bottom of this wave? What people are also looking at is like a common wave between different electrode sites. These are all interesting properties to look at if you're investigating the brain. So these waves, as I said, are internally generated, but they can also be externally generated. For example, you have experiments where your participant hears a beep, and as a result of this beep, some of these frequency properties change shortly after the beep. For example, about 300 milliseconds to 2000 milliseconds after the beep, some properties of the algorithm are increased, and they call it evoked response. So the Python library, as far as I can tell, to look at all of these waves and all of these different properties is called M&E Python. And this is what I try to use quite a lot. At least for the offline analysis. So far, I'm talking about analysis that is not really in real time, but you have all the data, you have all the time in the world, and you can look at the data and see what it's made of. Then a little bit more about signal and quality. So you can measure the brain signal from outside of the scalp. It is non-invasive. The signal quality is relatively poor, but you can quantize between maybe 2 or 3 different kinds of states in this way. Other methods or means used in BCI research is that you measure inside of the brain. It's a little bit more invasive because you need to open the scalp, actually put electrodes on top of the cortex or deep inside of the brain, or you put a microelectrogrid on the motor cortex. That is like the picture with in the middle over there. Especially with that method, you really have kind of like a high fidelity signal. So because you have so many tips, you have so many signals, you can do really cool experiments like exerting a real fine grain control over a robot's arm. So this lady has difficulty moving, and as revalidated for a surgical procedure, she has implanted one of these microelectrogrids on her top of her motor cortex, and with that she's able to very precisely control the motor arm, picking up like a can of a drink and allowing her basically to drink, whereas normally without such a procedure this would not be possible. So that is a nice application of BCI research. Taking things further, but I'm not going to talk too much about it, is the company called Neuralink. They really even more increase the amount of contact points you can put inside of the cortex. And what they're doing is really, really cool. And I just show you links so that if you maybe later rewatch this talk, you can find back one article talking about this approach, as well as a YouTube video that I can recommend looking at. So anyway, but for the rest of my talk, I'll mostly talk about the EEG, and the reason is because it's non-invasive, it's portable, and you can do it relatively cheaply. You don't have to spend a lot of money to do this sort of thing. Then some words on the real-time analysis. So how do you get the signal in real time? Well, luckily, it is a solved problem. And the package that you need to use is basically called Lab Streaming Layer. This is a C library with like ports to C++ and also Python. It allows you to extract the data in real time from many different kinds of clinical EEG devices, and you can like bring that into memory of your computer. So a little bit of example code. Basically, you import a library, you define an amplifier called amp, and then you have your while loop, and this is actually your neurofeedback loop, because this just keeps going on and on until you tell it to stop. And then you get a little bit of data with a get_data method. So that's the core of real-time data access in Python. And then, yeah, anytime you get a little bit of data, you get a tiny bit of data. So sometimes you get 100 samples of data, which can amount to 20 milliseconds only. It depends on how fast the loop is. Sometimes you get 200 samples. But anytime you get a little bit of data. So how this is used in BCI research is that you have the little bit of data and you need to decode it in some way. You need to figure out what it means. And with that you can help communicate. So you have these spellers. It's a certain experiment in which you have to look at a specific letter, and then using BCI approach you can figure out which row and which column are currently encoded, and then you can figure out what kind of a letter it is. You can use the brain signal also as an assistive method, where you help people drive around in a wheelchair, and there's a lot of work also going on in virtual reality. A nice movie I can remake is Avatar, which is that approach as well. So what you don't really see when you look at these approaches or when they are reported, that they do require a lot of work. So you need to do very careful pre-measurements where you kind of like train your decoder and also train your participant in order to operate these devices. So this is an active area of research. Another application of BCI is neurofeedback learning. So in some mental health disorders, for example, attention deficit hyperactivity disorder or depression, or if you have a persistent tonic ringing in your ear called tinnitus, experiments have shown that the brain rhythms are slightly kind of offbeat. So there's a little bit too much, for example, of the theta rhythm, there's a little bit too less of the beta rhythm. And the idea is that if you can normalize these rhythms somehow, you can restore normal function, or at least improve your lot in life, let's say. And the way to change your rhythms is through training. So training and conditioning is basically, as an analogy, if you are small and you want to learn how to walk, you see people walking, you want to imitate it. And you have kind of like a feedback loop that is really fast. So you try to take some steps and then you fall, and then your brain knows this. And it knows because your muscle has receptors, you have semicircular channels that immediately pick up if something is not going right. You also can take a look what is going on. And this feedback loop allows you to iteratively, through painstaking effort, at the end learn how to walk. With a brain rhythm it's less straightforward because you can't really see what it is, so your brain doesn't know. So the idea of neurofeedback research is that if you expose these brainwaves to the brain using a visual audio stimulus, you can, through iterative effort, learn how to change or increase or decrease some of your brain rhythms. And how that looks like is that you have a task. The task is like a threshold. The line is your current brain activity, like a rhythm, and people are instructed to push their brain activity over the threshold. And this is repeated, well, perhaps hundreds of times over a time span. Probably on the order of 6 weeks, maybe 10 weeks. Sometimes 20 sessions are used where people come into kind of like the clinics, do neurofeedback training for like half an hour, and then go home. Where each of the neurofeedback training is divided up in sizable chunks of maybe 5 to 6 to 7 minutes of training. So the idea is that you train your brain rhythm to normalize, and then you kind of like get the benefit. So this is the neurofeedback training. Research questions that you find quite common is like one of them is how much information can you extract from the EEG signal and what are good strategies for that. what are brain mechanisms that are involved, and research questions that I am most interested in is how well can people really learn to modify the brain rhythms, and is the neurofeedback learning really effective in everyone? For this, I use an MRI scanner to scan while the EEG neurofeedback is going on. That MRI part is a talk in and of itself that I'm not going to go further into. But now I'm going to talk about kind of like the frustrations that I encountered when I tried to do BCI research. So some of the obstacles that I encountered is that most labs have a neurofeedback setup with a very specific amplifier, very specific computers, with the stimulus software licensed. It runs only on Windows or it runs only on Mac, and it's kind of like impossible to do it anywhere else. And I would like to have methods that I cannot just do in the lab, but can just deploy anywhere. So if I want to collaborate with a different lab at a different location, I want to have the same methods that I use in my lab somewhere else as well. So something needs to be deployable. It will also be really nice to be able to teach. Like you can have the software on a laptop, maybe a cheap EEG system that you can give to a couple of students. You send them out in the field, and you can gather data. And this also allows you to reproduce like any findings that you have in one lab to a different lab. So, and then the programming language that come floating upwards more or less naturally is Python. Right? In order to deploy the neurofeedback approaches, I use Conda and Git. At the bottom, I show a link to an article that kind of like inspired me to do it like that. Basically, in order to deploy these Python approaches, is you go to GitHub, you download the Git repository. The Git repository contains an environment file, and then you can create the environment of Conda, and then you go into the environment and you can start. It's in practice not as easy as that, because there are sometimes problems. For example, if you're on edu-ROM network, then sometimes pip cannot verify the package that you want to download. So, but in any case, the main message is, in the end, this does work, and so I use this approach already to set up neurofeedback systems around Brisbane and also around Newcastle in Australia. So if I go to a lab, then usually they already have an EEG system. It's a computer, and the most complexity that you have is that the EEG net is connected to the computer, and the stimulus presentation computer sends some markers to the data acquisition computer. This is all offline, so no neurofeedback yet. In order to upgrade this system with neurofeedback approach, I use a switch with Ethernet cables connecting both of the computers to a real-time laptop. On the stimulation computer, I install like a stimulation environment that enables me to like show audio and visual stimuli. And on the real-time computer runs all the necessary tools to do real-time analysis. The stimulation environment the real-time data can flow through the network to the real-time computer, and the real-time computer also needs to send some signals to the stimulation computer to change the presentation and the stimuli. So the neurofeedback works with a neurofeedback stim environment. That's a Conda environment. It unfortunately still uses Python 2.7. The main components are CyclePy for generating all kinds of visual and audio stimuli, and coupled with that is a PIF package which takes care of the network traffic between the stimulation computer and the real-time analysis computer. Things also need to run concurrently, and for this I use Python 2.7's Asyncore AU, which is called Trollius. In the end, I would like to convert this to Python 3, but I haven't had the time yet. I use Spider to do edits and the stimulation also has a nice GUI in which you can select the different stimuli and change parameters before you start the experiment. These are the GitHub repositories where I find the software, so you can also get started. Yeah, with the PIF, how to steer it, it's like you can define an object called BCINet. You can ask it what kind of feedbacks are there, what kind of experiments are currently on the stimulation computer. Before the experiment starts, you can send signals that change the properties of your stimulation before you start. Then you can start it with the play command. And during the runtime of the experiment, you can send signals that will update your stimulation, for example, your line, with this send signal approach. You can also make other stimuli with it, and I give some examples of that. For example, this checkerboard, something where you need to follow the eyes. So let's see if we can go to the next slide. Right. Then something about concurrency and Trollius. I use Asyncore to take care of the concurrency. So sometimes you need to draw the stimuli on the screen while at the same time monitoring incoming network traffic that changes some kind of a property. The Asyncore loop doesn't really care if a function that you're evaluating crashes or not. So when I try this for the first time, things crash and have no error message to look at. And this is because this library is not made for experiments. It's made for handling network traffics, and if one of the incoming connection fails, it shouldn't care. So I made my own crash and burn protocol or methods. That everything goes through the methods, and if something fails, your loop crashes. And use some print statement to say error. In terms of Asyncore, yeah, network traffic is done with Asyncore, and this is a library that I don't understand. I want to convert it at some point, but well, if anyone has any helpful hints with that, then please let me know after the talk. Then the real-time environment. This runs on the real-time computer. It's Python 3. I use the Jupyter notebook because it allows me to use the cells to document the experiment, to explain what is going on, what the experimenter needs to be doing. It allows me to start the stimulation computer, to do real-time analysis, to start and stop the camera that I also have. And it's a really convenient way to iteratively go through your experiment. If something needs to be redone, you can just redo it again. These are the repositories that I use for it. The packages for doing real-time analysis is NFB Lab. I use the VM package, MD Python as well. There's OpenVibe, for which I also use some of the methods. And I don't actually use any methods from BCIPy, but it's a Python library which does real-time feedback, so I mentioned it here. Yeah, so this very shortly analysis pipeline. You see the neurofeedback loop that's as well true. You get some data from the amplifier, and you kind of go through analysis pipeline in which you select some channels, you apply a filter, you take an absolute value of the signal, and then at the very end you send it to the stimulation computer for display. And then the top figure is what you show on the real-time computer, and the bottom figure is what you see then on the stimulation computer. And in this way, the first neurofeedback setups are done. Oh, that's funny. Anyway, here are the repositories that I use. You can check them out. They're still a bit of a preview repository, so be kind. And with that, I would like to acknowledge some of my collaborators. There are guys in Brisbane on the left column. There are guys in Tübingen, in Magdeburg, and also some Finnish people and some Dutch people. And with that, I'd like to thank you for your attention.
Thank you, Johan. Okay, lots of questions already.
Mike, cool. So, thank you. Some of us might be wondering how we can get our hands on playing with some EEG neurofeedback without the budget of a neuroscience lab.
Thank you. That's an excellent question. I also encountered this problem because, I mean, the amplifier is the most expensive bit of equipment. For the rest, you just need a laptop. So I looked around, and there's this Open BCI initiative where you can... Oh, it's not there anymore. Anyway, and these guys, they make affordable BCI systems that also support lab streaming layer. So I actually ordered 2 of those, and with that I try to more or less deploy neurofeedback myself as well.
Hey, yeah, I just wanted to ask about the simulation thing you had where the brain activity was going up and down.
Yeah.
So is it that someone is watching the screen and when their brain activity goes below the threshold, they're shown some stimulation which is supposed to boost the brain activity so it gets up to the threshold and it sort of keeps it like that? Is that how it works?
So how it works is they're supposed to concentrate on their brain activity. If it's over the threshold for at least 200 milliseconds, and it's kind of like a threshold that you set, they are rewarded in a way because the experiment tells them that this is what they're supposed to do. And it tells them by making a little green patch that you see, oh, this is good, a little counter like increments, so that's also another signal. And they also hear audio tone. So all of these 3 things just tell the people, okay, this is good, do more of this.
How does someone make their brain do that?
The brain already naturally fluctuates in a way. So you set the threshold in such a way that they get about like 10 to 15% correct. And just by concentrating on it, then if people can actually learn how to improve the likelihood of getting more hits. And how the brain exactly learns it, that's a good question. That's also the thing that I try to look at with the MRI scanner. It requires a lot of repetition. And there are also people that don't really learn that well. So it's, yeah.
Hi. Is that right? Yeah. Let's say you want to build a machine learning system which uses neurofeedback to restore the normal activity of the brain for, let's say, tinnitus. How good is the EEG system to profile a brain with tinnitus and a brain with no tinnitus, or any other state, for example?
Could you please repeat the question? Sorry.
Yeah, so what's the quality of an EEG system to distinguish between a brain with a certain activity and another kind of activity?
I see. Yeah, to use machine learning methods for this is also an active area of research. I think you can get average effects. Like if you have a group of people with tinnitus and a group of people without tinnitus, you're more likely to figure out this brain rhythm at this location shows some abnormalities. It's quite difficult to do this at a subject-specific level. And I think that the quality of the EEG signal intrinsically might not be sufficient enough. It might be in some cases, but yeah, not always.
Do we have any more questions?
Thank you for the talk. So I've been noticing on the internet, there's been floating these things around called these particular types of music. I think they call it binaural beats.
Mm-hmm.
And they say it's supposed to stimulate certain brainwaves to help you focus. Is there anything to this? Is this actually like a legit thing?
With these systems, I can imagine that like your brainwaves kind of like follow a stimulus that you give. For example, if you show people a checkerboard that alternates with 10 times per second, your brainwave will imitate that also with 10 times per second. In terms of like music and with these beats, I would be a little bit skeptical. I would like to measure it and validate it before I say something about it.
Well, that's all we have time for today. So thank you again, Johan. And
Thank you.